Yeah, thank you very much for this kind introduction and the chance to talk to you all guys here. So I want to talk about a few things today. First thing is I want to talk a little bit about data science in general at Netflix, what we are doing. It's a new group that has been growing and will hopefully be growing much more in the future. Then quickly a recap of the Netflix prize competition. In case you've forgotten a little bit about it, it has been now a few years. Then I want to motivate why recommendation is actually a ranking problem. And then there are two aspects that I find very important when it comes to ranking. So one is that the ratings are not missing at random. So that's then the first technical piece. And I want to introduce the top hit rate as a testing measure, and then how to train to optimize it. And then the second part is about the popularity bias, another important aspect of the ranking problem. And then there are many more, but I want to focus on those two. So this is probably the part that you're most familiar with. At Netflix, in data science, we do recommendations. So we have a catalog of movies and TV shows. And we want to make personalized recommendations to the users. And key challenges nowadays are that we have a lot of different data sources. At the Netflix competition, we only had ratings. Right nowadays, we have play data when people watch something online. We have also tag information about the movies. We also know what we have recommended to the users in the past. And often people actually follow what we recommend to them, right? So there's this feedback loop that what we recommend, they may play. And because they play it, we have in our training data those plays. And so if you just basically then recommend again what they played, then we are just sort of trapped in our own recommendations. So then the other part that people are working on is actually we also have to decide what movies and TV shows we actually license so that they become available on Netflix. So we are also taking some data-driven approach there, analyzing what do our customers like, and based on that we can determine actually how much should we pay for certain movies if we buy them, or should we buy them at all. Another part of our group works on the data-driven optimization of the streaming platform. Because the bandwidth can change over time, and so if we can actually predict ahead of time that your bandwidth dropped, for example, we can avoid the rebuffering and things like that. And then finally, we are also doing some data-driven marketing, so that's about the online ads and all the bidding process that is behind that, so that we can actually get some new customers. Okay, so let's quickly recap the Netflix prize competition. So it ended a couple of years ago, and what we had is we provided a big data set concerning users and shows. And whenever a user gave a rating to a show, he could pick a value between 1 and 5 stars. So 5 is the highest rating. It means they loved it, and 1 star means that they didn't like it at all. Key properties of the data set were that it was very sparse, so it's 1% of the user item pairs have a rating value, so 99% of this matrix is empty. So for recommendation problems, that's actually quite a lot of data, quite dense. And the sizes was approximately 500,000 users, 20,000 movies, and 100 million ratings. And so from that data, the challenge was then to build some recommender systems. And there are basically two types. So the content-based recommender system. So the idea there is that you use some information about the movies, right? So you know who are the actors, the genre, and all that stuff. And based on that, you make your recommendations. And then the second type is collaborative filtering. And here you only use the information what did actually people rate and with which value. And then you basically look at, in this big data set, you look for similar users, for example, who rated the same or similar movies, and based on that you make your recommendations. So you're not using any information about the movies in this case. And this turned out to be the more successful approach in the Netflix competition. I'm also focusing on that one and in the rest of the talk. And then once you have a recommender system, you want to test how well it actually works. In the Netflix competition, the accuracy measure was the root mean squared error. And the idea was that in this test data, we also have some items rated by a user. And the way we calculate it is we have the actual rating in the test data, and we have the prediction from the recommendation system. And then we just take the squared error of that, and we sum up the squared errors. And of course, we can only do that for the observed ratings in the test set. Otherwise, we don't know the true rating value. And that's the root mean squared error. Okay? And so that's, in a nutshell, the Netflix prize competition. And now I want to motivate why the recommendation problem is actually a ranking problem in reality. And yeah, so I think the good reason for using the root mean squared error was that it's easy to compute. And probably for that reason, it has become the most popular accuracy measure in the literature. Still nowadays, it's mostly Rmse, but I think ranking measures are picking up now. And one example where you can see that there are some limitations to Rmse is in this table. So let's just assume that we have some horror fans and some romance lovers as users, and we just have some horror movies and romance movies. Okay, and the behavior of the users, as you can see here, is that if they like the movie, they give it a 5, here and here. And if they don't like it, or if they may not even know about the other movie, they just don't have any ratings here. So you can see these two clusters. Another question is, let's say, for this user, which movie would you recommend? Right? And there are now two basic answers. One is that if you optimize Rmse, right, then you could just say, okay, the simplest model that gives me a perfect prediction of 5s is the model that predicts a 5 everywhere, right? So also over here, all the 5s. And if I have to pick one movie, then I could just break the ties randomly, and I just randomly pick one of those movies. So that would be one approach, right? May not be the best approach. The other approach could be like to say, okay, even if I don't know this information about horror fans and horror movies, I can see two clusters here. And because of that, this seems to be the best candidate to be recommended, right? And what's the basic difference now between these two assumptions, if you can recommend any of those, or if you should actually recommend this one? What's the better recommendation? And it boils down basically to the fact if the users actually rate these movies at random or not. And so there was an interesting study that was done at Yahoo, and they did it with songs, not with movies. But I think in general, their results carry over to a lot of domains. So what they have done is they had a lot of songs, and they collected ratings, but they did that in two different ways. And that's the key thing. So on the left side, Yahoo actually randomly picked some songs for each user and asked this user to give ratings. And because Yahoo randomly picked those songs that the user had to rate, so we can assume that's a random subset, and this distribution that they get is a good approximation to the true distribution of this complete data set that we don't know. And what we can see is, among a random set, a lot of people just don't like the movies, right? Or the songs. And then they collected the ratings in a different way. That's on the right side. And that's the way how typically the ratings are collected. So here, the user was free to choose what songs to rate and then give a rating. Right? And so what we can see here, this distribution is very different from that one. In particular, the low ratings are now much less than over there. Right? So it's almost here a uniform distribution. So that means people don't give low ratings typically, so what they do is they just don't give a rating at all instead. And now by comparing these two histograms, we can see that they're very, very different, and that means that the ratings that we can observe in these data sets that we get, that this distribution doesn't really reflect the true distribution, right? Because we can assume this is a pretty good approximation to the true distribution, because here we really have a random sample. So the challenge now is that we have this data set to train our recommender system and also to test our recommender system offline. But how well this recommender system performs in reality, how good the user experience is, basically depends on this true distribution over there, which we actually don't have. And so that's the key challenge, that we have to deal with this data, but we need to be good on this distribution over there. So to have a more conceptual view, you can just think of it that there is some data for the users and for the items, and this is this unknown complete rating matrix, right? So it's the complete data that we don't know. And then we observe some data over here. In Netflix case, 1% of the data. And there is some missing data mechanism that determines actually what we observe here. And there's been a lot of work about missing data mechanisms, so famous work by Rmse many, many years ago. And in the context of recommender system, there's been some work also by Mellon. And the key point is, if the rating is missing at random, so that's the easy case, because that means then the fact if we observe the rating or not doesn't depend on its rating value at all, right? And the thing that makes it easy is then, if that's the case, then we get the correct result by doing our analysis by just ignoring the missing ratings, and we just work with our observed ratings. But as we've seen on the previous slide in this histogram, that's unfortunately not the case. And so we cannot ignore the missing ratings. And so that's why the key thing is, when we want to now develop our approach for ranking, we have to take into account that these ratings are not missing at random. So that's the key thing. And that's also one of the main problems that I think the root mean squared error has, because it's a root mean squared error on the observed ratings. So you're implicitly assuming that the ratings are missing at random. And also among the ranking measures, there are many measures that cannot really deal with missing ratings. But one that can do it is the top K hit rate. And it's defined as follows. So the idea or the real world problem is that you have this catalog of all the items that you have, right? And then out of those items, you have to pick whatever number, let's say 5 or 10, that you can actually recommend or show to the user, right? So you have to pick a small number out of all your items. So the key is out of all items, not about the out of the items that have a rating also, but out of all ratings, out of all items, you have to pick a few and show it to the user. And that's exactly the idea of the top K hit rate. So what you do is you have all the items, you calculate a score for each of the items based on your recommender system, then you rank it based on that score, and so then you get this list of all the items. Then you look at the top K item, and this K depends on your application, right? If it's a Google website, it's maybe 10, because nobody switches to the second page. And then you look at these top K items, and then in your test data, you can see now what people actually liked. And so if this user now liked 3 items, and 2 out of them are in the top K, and 1 is not, then the top K hit rate for this user would be now 2/3. And that's exactly the definition of top K hit rate. It's also called recall. And then there's another measure related to it, it's precision. And in precision, you also take these 2 that you actually hit, but then you divide it by K instead of by the number of relevant items. So a lot of people like precision better than recall. But one thing to remember is when we have a fixed data set and a fixed k, then both of them are actually proportional to each other, right? Because upstairs we have the same number, and downstairs we have different numbers, but on a fixed data set, this and this, so on a fixed data set, this is fixed, and for fixed k, this is fixed. So if we always use the same test data and the same k, right, then better precision means better recall, so they are proportional. But the key thing that I find nice is, under very mild assumption now, when we calculate now recall on our data where the ratings are missing not at random, right, on this histogram on the right, when we calculate it on that distribution, under mild assumption we can actually get an unbiased estimate of the recall on this unknown complete distribution, which we don't have. And the simple assumption is that now the relevant ratings are missing at random, and by relevant ratings I mean the ones that indicate that the user really liked the movies. And in this case we can pick, let's say, the 5-star ratings. That means they really liked it. So I assume now only that the 5-star ratings are missing at random, whereas the 4, 3, 2, and 1-star ratings can be missing with different probabilities, right? Which is obviously the case. So this may also not be the perfect assumption, but it's much milder than assuming that all the ratings are missing with the same probability at random. So, and the reason why this assumption then actually gives us an unbiased estimate is simple, because then we, in this case, we would have now, let's say, 10% of the relevant items are observed here, and 10% are also observed here, right? And then the 10% actually cancels out. And so that's why you get then the correct number. So the absolute value of recall has some meaning, whereas for precision, for example, you wouldn't have this case, because if you have now observed only, let's say, 10% of those, but you always have the same k, then your precision looks much smaller than it actually is. Okay. Okay, one more thing is, as you can also see now, as the k actually gets bigger and bigger, right? If you put the bar lower, then your hit rate will go up, or recall. And so that gives you then this curve here. So k is now normalized to the length of the entire catalog list, so just divided by n. And then as k gets larger, then just the top k hit rate gets bigger and bigger from 0 to 1. And then what you can also define is, you can just define the area under that curve as your new measure of the ranking quality. And then you basically get rid of a particular value k if you don't want to specify a particular value k. And it turns out that in leading orders, this area under the curve is actually, in leading order, approximately the same as the area under the ROC curve. And again, it gives you, like before also, it gives you an unbiased estimate for this data that is missing, not at random. So that's nice. And so in my slides coming up, I just use now this measure as my accuracy measure. And so how can we train now our recommender system to actually get a good ranking result? So what I use is just matrix factorization model. That's one of the best models that came out of the Netflix prize competition. I just use also the same model. So the idea is that the predicted rating R hat is just an offset value Rm, so it's just a number, plus P times Q, and these are just two matrices here of a low rank, 50. And so basically for a given user and a given item that I want to make a prediction, I just use this vector of the item and the vector of the user multiplied together to get my prediction. So the question is now how to train this model, because what I need to do is I have to learn all these entries here from training data that I have over there. Right? And once I have it, then I can make my predictions. Okay, as training, I use actually something that is almost the same as has been used in the Netflix competition. So I'm minimizing a squared error here. And I do that for computational efficiency, because minimizing squared error is really efficient. So here we have again the model. the matrix factorization P times Q here. This is the rating value. And I take the difference and square it up. Then I have some standard L2 regularization term here, just forcing my entries in the matrix P and Q to be small. And that's determined by this parameter lambda, how much I want to force them towards 0. And the key difference is now, like with the top K hit rate, where the goal was to look at all the items in the catalog, and then you wanted to see how many you actually get into the top K. So the key thing is that you actually want to account for all the items in the catalog, and that's exactly now what is the difference to the standard Rmse training is that I'm summing over all users, but then also over all shows. So not just over the shows that have a rating, but over all shows, right? Because I want to take into account all the shows for a user, like in the top K hit rate. So if I do that, then the problem is that this rating value that I have in my training data, right, is not defined for all the ones that don't have a value. So I have to do something about it. Simplest solution is that I just impute a value for it. That's this little Rm. So if it's missing, I put in a little Rm here. Same Rm as over here. So that means then they just cancel out in case it's missing. And then if you want to view it from a regularization perspective, it's just like I have another regularization term in here that also P times Q has to be small, not just P and Q by itself. So now the other problem is if I impute now these little Rm values here for all the missing items, then because 99% of the values are missing, then I'm basically just summing up here, right, all these squared errors regarding my missing entries. And so I'm mainly learning from my imputations, not from the actual training data. And to take care of that, I have now a W for each item and user. And this is now a 1 if this is actually a observed rating value, so that I can learn from it. And if it's an imputed value, then this is a small value, little Wm. And so the idea would be then that I make a more balanced data set for training, right? That's typically a good thing. That maybe half of the training data is my real rating values and the other half is the imputed values, right? And because the imputed values are so much more, I just give them, each of them a smaller weight. Or you can also see it in a different way. The other way of seeing it is that I impute a value here for the missing ones, but then with a small confidence, which corresponds to a small weight. Right? So that's the idea. So the idea is now basically to minimize this objective function and to choose now a lambda, a little Rm that I impute, and the little Wm for the imputed ratings, so that I actually get the best performance for the top K hit rate on the test data, right? Because eventually I'm not interested in minimizing this squared error. I want to get the best top K hit rate on my test data. And now what do we get? So I tried now different values of imputing the rating value for the Netflix data, and I got this curve, and this curve is obtained by then optimizing the other values, the Wm and the lambda. And what you can see now here, so this is a range of rating values from 1 to 5 that people can actually give. 3.6 is the average rating value in the data. And now what you can see is that your area under this top K hit rate curve actually goes up a lot when you actually impute a smaller value. And so the optimum is at around 2, but theoretically you could even impute something that is negative. But this actually is intuitively a really nice result, because it basically means, if you think of these histograms before again, is that this histogram on the left side had these high numbers of ratings of 1 and 2, right? And that's exactly actually what you can see here also, that if people don't give a rating, actually it means that they give maybe a rating of 2 on average for those missing ratings, right? So that makes a lot of sense. Then the more interesting thing is now actually looking at the weight that we have to assign to these imputed rating values. And you can see here now the entire range of weights that I tried out. So if you are over here, you choose a weight of 1. For each imputed rating value, that means then the observed rating values have a weight of 1, and each of the imputed ones have a weight of 1. So that's the standard SVD that you would do then. Each entry has the same weight. So it's exactly the same as has been done for latent semantic analysis. And then you get some result here, maybe 0.91 or so for this area. And then interestingly now, as your weight decreases, your ranking result actually gets better and better. So that means actually now going to a more balanced data set, so the balance between imputed and actually observed rating values now becomes more and more balanced. But the interesting thing is now you at one point get an optimum, and this optimum is at 0.005 for the Netflix data. Right? So it looks like it's almost 0, but you actually have to compare it to the fraction of observed ratings, right? And 1% of the ratings is observed. And so compared to that, you can see now that the total weight for all the imputed ratings is half the weight for all the observed ratings. So in the end, you actually end up with quite a balanced data set where the actual observed ratings have twice the weight compared to all the imputed ratings, right? So exactly what we intended. So that gives you the optimal value, and then the interesting thing that happens if you really go to the weight of 0, which is then the case that you are actually ignoring the missing ratings. Right, so that's a standard RMSE training. Then actually it drops off a cliff and it comes down all the way to here, which is actually below the green line. So it's actually the worst result that you can actually get is with a weight of 0. So it's even worse than putting a weight of 1 there. So that's what I found very interesting. So you have to get close to 0, but not too close. Okay, so that was now all the results for the area under the top K hit rate curve. So we can also look at the top K hit rate curve by itself. And again, so these numbers are normalized, K from 0 to 1. So that's normalized for the length of the catalog. So that means the end of the catalog. And typically you're interested in having good recommendations at the very top. So that's why I zoomed into the top 2% of the items. And you can see here, so this is a model trained to optimize Rmse. That's the one with the imputation. And you can see there's a huge increase now in the top K hit rate. At the same time, you can also see Rmse is actually getting worse, in case you're interested in the Rmse. And this is now a comparison to the work that Yehuda Koren had published in 2008. So that was on the way to winning the Netflix prize, right? So he's one of the co-recipients of the Netflix prize. So he showed in that paper, among other things, that as you increase or decrease, so you improve Rmse with the different models that are the different lines. So as you improve Rmse, you also get better top K hit rates. So that was one argument why, even though Rmse seems not to be the right measure, but improving Rmse also improves the top K hit rate curve. And so he got it for the entire catalog, and also for the top 2%, he gets these curves. And so that's an integrated model, the best here that he has. I think at that point it was 0.887 for Rmse. So that's a really good Rmse. But what you can see is you get better top K hit rate results, but only up to a limit, right? And then if you actually account for the missing ratings, so for the fact that they are not missing at random, or that they're missing at random, then you get this other big improvement. So here basically you're only using the information about the different rating values, and as you use this information better and better, you get obviously some improvement, but then you don't get beyond a certain limit, and if you want to go beyond that, then you have to take into account that there's additional information in the fact that what has been rated by a user, so that it's not missing at random. So that's the interesting thing. So even though I used a very simple matrix factorization model, but just taking into account that the ratings are not missing at random, then I actually could get 39 to 50% larger top K hit rate compared to a really sophisticated model that optimizes Rmse. So that shows that ranking is a very different story than optimizing Rmse. And now I quickly want to go to the second part. That's about the popularity bias, also in the context of ranking. So the problem is as follows. So not every item has the same popularity, right? So there are some blockbuster movies and some other movies that nobody actually watches. Same thing for songs or books. And so you can just measure the popularity somehow with clicks, purchases, or ratings, and then sort the items based on how popular they are. And then it turns out that there are a few items that are very popular and many items that are not so popular. And so you can just arbitrarily put a line somewhere, maybe so that you can more easily talk about the head and the long tail. Typically this head is pretty small, can be maybe just 1% of the items or even less. And the challenge now with the recommender system is that in the head, you have obviously a lot of data, a lot of clicks and the ratings and so on, but at the same time, people may already know these movies. So recommending those movies may not be super helpful for the user, but on the other hand, your system would be probably really accurate there because you have a lot of data. At the same time, in the long tail, you have the opposite situation that the items are probably unknown to the user, so it would be very useful to recommend them to them if they fit. But at the same time, you have less data here, and so you have lower recommendation accuracy, right? And so that's the problem. The question is now, how do you find a good trade-off between the recommendation accuracy that obviously goes down as you go to the long tail, and at the same time, you actually want to go to the long tail a little bit. And so you have to somehow combine these two so that in the end you get maybe some recommendations that look like on the red line. And the idea is the following, that I just look at the relevant ratings, right? In this case, the 5-star ratings. And what you can see here is, again, a plot where I have the number of 5-star ratings, and here the number of movies, the count of the movies. And you can again see this is a plot that shows you that there are some movies that are very popular, get a lot of 5-star ratings, and a lot of items don't get a lot of 5-star ratings. And in this log-log plot, it's almost a straight line, which means it's a power law and good approximation. And that's in the observed data, right? Conceptually, we can think of now what happens now in this complete data set that we don't know, or what distribution do we get over there. So in the previous part of my talk, I assumed that the relevant ratings are missing at random. So that would mean that over there we have exactly the same distribution as over here, right? And now we relax this assumption a little bit. So maybe the probability of observing a relevant rating also depends on its popularity, right? Because if something is popular, you know about it anyways, and so you're more likely also to give a rating. The other effect could also be this feedback loop in our recommender system, right? Because something is popular in our training data, the recommender system learns that it's popular, so it recommends it to you. And because it recommends it to you, you play it. So in the next round, the training data contains even more plays for this item. It becomes even more popular, and so the popular items become more popular, right? So we also have to do something about this feedback loop. So there might be a lot of reasons why probability of observing a rating depends on its popularity. And so what we can do is just assume that there's a power law with an exponent gamma. So because if we assume a power law here, and we have a power law here, then also this is a power law, right? So we can just assume that, okay, maybe the distribution here follows the same distribution as here. So we have all power laws. So assumption now is that the probability of observing a rating is proportional to the number of relevant ratings in the complete data with some exponent gamma. So the problem is we don't know the complete data, but a few lines of math actually show us that we can rewrite it then, that this probability of observing a rating is proportional also to the number of relevant ratings in the observed data that we have, but now with an exponent beta, which is between 0 and 1, and it's related to gamma, just having gamma divided by gamma plus 1. So now we can actually calculate this probability of observing a rating. And now we can define our refined top K hit rate or recall. So we can just do now some popularity stratification. Now what we do is we don't count a 1 for each hit, but we just count the weight, and the weight is proportional to 1 divided by the probability of observing the rating. And so this is now for the items in the top K, and this is now for all the items in the list, which is the definition of recall. And yeah, and now we have actually a way to quantify the popularity bias in this accuracy measure. And there are obviously two extreme cases. If beta is 0, then we are back to the original case that every rating has the same weight. Or if beta goes to 1, then the other extreme case that every item has now the same aggregate weight because of this 1 divided by the popularity. And probably we need something in between. And there are two applications, of course. The one is that we can just correct for this popularity bias in our data. And for that, we would need the true value of beta. If we had it, we can just then use it, and then we would get, again, an unbiased estimate of recall for the complete data. So that's nice. And this approach is kind of a standard thing that has been done in the literature of non-response in surveys a lot. If you're familiar with that, it's also going under the name of propensity, score rating. And the other application is we can also now get recommendations from the long tail simply by overcompensating now for this popularity bias. We just take an even larger value of beta than would be the true value. Okay, so then a few experiments. Again, I use the same matrix factorization model as before. And then in the first step, I train it exactly the same way again. And remember, we have this weight here where we have a 1 for the observed values and a little wm for the imputed ones. And so in this first experiment, I just have now different values for the imputed ratings. This is the optimal value from before, but then also smaller values by a factor of 10. I have the matrix factorization optimizing root mean squared error also in here, and the singular value decomposition, the standard SVD, and bestseller list, that's just the popularity. So first interesting thing is to see here is actually that this Rmse-based matrix factorization model is about the same as just an unpersonalized bestseller list, which is kind of strange. And what you can see now is that as you increase beta, so you are stratifying for the popularity and you're going towards the long tail here, what you can see is now these methods that favor popular items to be recommended, especially SVD and bestseller lists, that they actually drop down, they are much worse. The other thing is that even in the extreme of beta equal 1, it's actually better to impute the missing ratings, but now with a smaller weight than it was optimal before. But it's always better to do it than to ignore it. And what you can also do is now you can just look at the top 20 hit rate and how it changes for different betas, right? As we go from beta from 0 to 1. And that's plotted now in this graph, so that's a solid line here. And now what I do is I train now my matrix factorization now in a different way. So I don't have this constant little wm anymore, but now I change this little wm. And in the first case, I do the same thing as in my test top K hit rate in my stratified recall. Now my weight for the observed ratings is now proportional to the popularity or the inverse of the popularity to the power of this exponent beta. So this is just basically replicating exactly what I do in the test now in the training. And if you do that, you can see now these curves that I have here now, besides the solid one. So these are now for the different values of beta. And this is, for example, for training with beta 0.9. And you can see that training with beta 0.9 is the best if I also test with beta 0.9 or 1. Whereas the beta 0.5 training, which is this curve, is about best for testing with beta 0.5. So if you train with a beta value the same as the test beta, it seems that gives you the best results. But in particular, what's interesting, you get a big improvement over here. Alternatively, what you can also do is instead of increasing now, or instead of decreasing the weight of the observed ratings, you can also just leave the weight as 1, and you do the opposite. You increase the weight of the missing items that you impute, and then you get very similar results. It turns out that these results are slightly better than those, but not a very big difference. So now in summary, basically what happens is that we have the model trained with Rmse, and then we get a big improvement to the blue line for small betas when we account that the ratings are not missing at random. So that was what I talked about in the first part of the talk. And then when we now also train now with a model that has a beta in there, then we actually get a big improvement now for the long tail part of the recommendation. So this is now giving a big improvement for the popular recommendation, and this gives you the big improvement now for the long tail recommendations. So then in the end, with these models now, you are everywhere actually much better than the Rmse model. Okay, so then, yeah, just maybe a few more plots here, and then I'm done. So this just shows you the popularity distribution in the training data. So this shows you how popular items are in the training data, and then these two curves show you in the top 20 recommendations, how often do actually these items get recommended. And as you can see, this blue curve is the one with beta 0.9. So if you train with beta 0.9, then also the things that are less popular in the training data now actually get recommended more often in the top 20. So here you can really see, as you crank up the beta, you get recommendations more from the long tail, whereas the model trained with Rmse is kind of all over the place, and it's not so nicely aligned with the popularity of the items in the training data. Okay, so the catalog coverage also goes up a lot, so let's just skip that a little bit. Okay, last thing is, we don't know what's the optimal value of beta, right? That's the open question, so we know how we can change it, but not what's a good choice. So I did a little user study, and so what I did is people could just rate some movies, and then they actually get instantly some recommendations. So 20 recommendations per page, and they could actually click on the next page if they wanted. And in the end, they got asked to rank the different recommendation systems. So they had basically a drop-down menu where they can change the recommender system. So there were 5 recommender systems. They didn't know which one was which. And they could just change it and see then which one they like better. And then keep on rating things and changing recommender system. And so in the end, they had to tell me how they actually like the different recommender systems, give a ranking of the 5 systems. And what I did is I had 4 systems with different values of beta from 0 to 0.3, 0.6, and 0.9. And I also had the Rmse-based one. And then as you can see here, so the average rank of small beta values, but maybe a little bit away from 0, was much higher ranked than the other ones that had recommendations from the very long tail or Rmse-based recommendations. And the little test that I did actually turned out that even though I had only 20 users, because the difference was so clear that I got a p-value of 10 to the minus 6. One thing that I should also mention is that in this little user study, there might be a little bit of a bias towards smaller betas because it was a new recommender system that people used. They were not familiar with it. So you also have to build up trust. And you typically can do that by recommending some more popular items, because then people recognize it and say, oh yeah, I know that. Whereas if you recommend more from the long tail, then people don't know the items maybe, and then it's a little bit harder for them probably to trust the system. So that's why there might be a little bit of a bias. Another thing is also the optimal value of beta probably depends on the domain. So this was for movies, or for songs, so other items might be a little bit different. Okay, so last slide. So what I've been focusing on in the last couple of years was taking care of all kinds of biases that are in the data set. So starting out with the root mean squared error, that is the most popular measure. Right, one has to realize that's on the observed ratings. Then there has also been some work on using ranking measures on the observed ratings. Key point is that all these approaches assume that the ratings are missing at random, so that these two histograms are the same, which is obviously not the case. And so the first step was then that I assume, or worked on ranking measures on all items, right? And then my assumption was that these relevant ratings are missing at random, which was already one step forward. And then the next step was now popularity stratified recall, where I now also try to distinguish among the relevant items, in this case concerning popularity. Okay, that was it. Thank you very much for your attention. I'm happy sorry, I'm also recovering from a cold right now, so it's catching up right now a little bit. Yeah?
So you try to predict the missing ratings, right? The question to what extent it's true to the rating nature. Some user rated really low. So if you try to group users in beans, those who rated a little, those who rated more, those who rated a lot, you might want to see that this distribution try to asymptotically get to your optimal distribution, which you try to reduce. Is it really true? Or maybe the real life is not exactly close to what you try to predict in the long term.
Yeah, so
the ratings of users who rated more than 2,000 movies should be closer to your predicted listing than those who rated a little, right? Or wrong?
Yeah, I mean, the one thing that makes everything a little more complicated, that everything is personalized, right? So if you have now users who have rated more, they may also have a different taste than people who rated less or so. So that's why it's a little bit hard to say now, okay, people who rated a lot, I use their distribution as a better approximation to the true distribution. So that's, I think, the key challenge in that. But yeah, I agree, one could maybe get a little bit more information concerning this problem by maybe stratifying and the users based on how much ratings or how many ratings they gave. Yeah, but I haven't really looked into this detail. So I have done one thing where in this case, for example, I actually have split the users based on how many ratings. Actually, not how many ratings they have given, but I have split them based on how popular the items are that they rate. So if people are more interested in popular stuff or not so popular stuff. And I have found basically no help or no additional information to actually improve the recommendations, without going too much into the details here. But that wasn't really helpful. And so, yeah, one has to see. Maybe it helps, but maybe not. Yeah?
It seems like there's two different kinds of missing data. The missing data that's missing because you saw those movies and didn't want to watch them, and movies that you just haven't discovered at all or haven't looked at. And I'm wondering, since you have the data to look at that, if you explicitly create a model with two different types of missing data, if that helps at all, or if it's just too little data to matter.
Yeah, that's a very good point. Yeah, so if you have the data that you can distinguish between these two cases, then you can.
Have it, right?
Yes and no, but typically you don't have it, right? And then you have to do an approach where you cannot distinguish.
Right.
In our case, yeah, so we have the information if people watched it on Netflix and then if they rated it, right? But a lot of people may have also watched it maybe outside of Netflix and then they rated it.
But don't you also have just the data where they look at it, like you can tell that they've seen it but not clicked on it or something?
Yes.
That's also.
Yes, so that's something that we are working on also right now.
The caveat is that all this work was done when he was in Bell Labs,
Yeah.
and so he didn't see that.
That was
data
work
at that point.
actually that got me the job at Netflix. Yeah. but now at Netflix I have much more data. I can do actually much more interesting stuff. Yes. Hmm?
I thank you for the lecture, and I have a question about the evaluations. Means that we try to introduce a new evaluation method to reduce the bias from the popular item with unpopular items. But sometimes I guess it's very my experience that people sometimes they do not rate something not because they do not give them the rate, because they do not care. For example, people might provide bad ratings if they do feel like they do not want this item to show up in the recommender system.
Right.
So in that case, I think you're trying to build a new evaluation method to help to have a better rating for the missing items. But in fact, maybe users do not care about those small parts. They maybe only focus on some popular item or only the item they're interested in. Is there any evaluation to see whether user how do you measure the bias of the user among the popular item and the unpopular item?
Yeah. So. I mean, again, in this experiment, I measured what's the average popularity of the item that the user rates. And I didn't really found that it was any helpful. But I mean, one thing that you could also think of is, I agree that sometimes people hate a movie, that's why they give a rating of 1. And that has some useful information. And maybe that's also the reason why in the end, the optimal value to impute is, for example, a 2, right? So I'm not imputing a 1. I mean, 1 would probably give you almost similar results, but I'm only imputing a small rating value, meaning that they don't like it, but at the same time, I impute it with a very small weight. And the small weight means that you have a small confidence in this rating value, right, that you impute. Whereas if people really give a rating of 1, then you actually would use also a weight of 1. And so that would be a very highly weighted, high confidence value of 1, and tells then the recommender system you don't like that item.
For example, if I shopping on eBay,
Yeah.
one recommender shows up I might rate 1 on some nuclear material, and other item will show rating 2 on the same material. But really, the user might not care whether they provide accurate rating for the items they do not care. I think if you
Exactly,
focus
yeah.
on the long tail ones, maybe that's not what user wants.
Yeah, exactly. So that's why I evaluate then the method only in the top K, right? So I don't really care how good the recommender system is at the bottom, but imputing some low values in the training actually helps you a lot also to be good in the top. And the simple reason is the following, like in this example that I had at the very beginning here is, right, so for those people who like romance movies, if I actually impute that they don't like this part, that helps me a lot to make the recommender system focus on romance movies for those people, right? Because, again, if you optimize Rmse, for example, right, you would just have a system, for example, that predicts 5s everywhere. So then you could easily predict something really bad for the users as well.
But if we try to evaluate Rmse, we evaluate them by real user ratings. But the user
Yeah.
might only rate the items they care, so maybe the Rmse might focus more on the frequently rated items. I think that might be closer to user needs. But for the ATOP,
Yeah.
for example, they focus on rate accurate on overall the items. But for example, user might only focus on a small part of it.
Yeah, so I think the question is what's the goal of the recommender system, right? And I think in reality the goal is that you want to do some ranking. You want to pick a few items out of all the items that you have, and the other goal could be maybe predicting the rating value of a user that he would give to a movie. But that's a different thing. And often people say if you minimize Rmse, then you are focusing on predicting the rating values. But that's, I think, also not completely true, because if you think about it, what you are doing is you are optimizing or you're learning the probability of the rating value given that the user has rated it, right? Because it's conditioned on the fact that you have the rating. Because you're training on the observed only, so you are testing on the observed values only. So it's conditioned on the fact that you have rated it. But if it's conditioned on the fact that you've rated it, right? So that's the probability you learn. Then why do you need a model actually to predict the rating value given that the user has rated it? Because you can just look it up in the database, right? You would actually need a model that tells you the rating value conditioned on the fact that the user has not rated it. But that's not a model that you're actually learning when you're always learning on the data that you have, right? Because then it's always conditioned on the ratings that you have given. And so that's the tricky part. So that's why I think optimizing Rmse doesn't even actually give you a good prediction for the rating value, because it only gives you a good prediction for the rating value conditioned on the fact that you've rated it. But then you don't really need some prediction, right? So, yeah.
So I'm thinking in terms of position bias. So, meaning traditional like web search, maybe this is just my hunch that like it's like more easy to kind of like determine whether a particular rank result is good or not, just by clicking on it and getting a summary very quickly. But it might be kind of like more challenging in case of like movies and TV series, and like without going through like half an hour to 1 hour, difficult for me to know whether that's useful for me.
Right.
So it seems like position bias is going to be even more crucial in these kind of scenarios than kind of traditional web search. So I wonder whether it will help a little bit.
Yeah, so the position bias, you mean where we present it on
Right,
the
and
on
so
the
you're likely
site.
to get maybe more feedback.
Yes.
from top
Yeah, so I think that's a very relevant problem, and it's even more complicated on our Netflix site, because on Google, right, you have a list, so it's a linear list. People assume a model where you go down from the top of the list, right? If you click on the fourth element, then you didn't like the first three, something like that. It's often an assumption. So we actually don't have even a linear list on our website, because it's actually a two-dimensional array, right? So you can, and then we don't know, does the user actually read line by line, or you go down, or you go somehow from the top left corner and go down and go left? I mean, yeah, how do you actually go through it? It's even a little bit more complicated in our case, and so even a little bit more difficult to model then, because it's not just this.
Well, for another reason too, right? Because in Google, a query determines the context for the most part very clearly, whereas when somebody just logs on to Netflix, I mean, they could have so many different moods, you don't know what their mood is at that point. So there's not I mean, the way it's organized is organized to cover the most bases as far as what your mood might be. So just because you skipped on the first row and that talks about horror movies, doesn't mean that you hate horror movies, it just means maybe that you were not in that mood for that time. So it becomes much harder to estimate position bias. Though we do try.
So I'm curious if there's any disconnect between ratings and what people actually watch. Like, Schindler's List is a great movie, and I very rarely want to watch it.
Good point. Yes, that's true. Yeah. So now that so I was talking all about ratings, because, as I said, that was work before I joined Netflix, and I had only the rating data. But now we mainly work with play data, because streaming the movies, watching it online, is the main focus of our work. And so if we actually compare, just simple things. What has the most plays, right? What's most popular concerning play data? What's most popular concerning rating data, for example? So we can see there's actually quite a big difference, And so the main difference is that it seems that there are some high quality movies that people rate very highly and are very popular in the rating data. But at the end of the day, these high quality movies are maybe too tiring to watch, so people often then go for a cheap TV series also and watch it, because when they come home they just want to watch something easy.
Actually,
and so there's actually quite a little bit of a difference. So we are actually nowadays working mainly with play data, not with rating.
So there's an interesting anecdote for this, right? So we're trying to, when people become members of Netflix, we ask them to rate a few movies, so we kind of get an idea of the taste. It turns out that people often rate movies that make them look good, so they rate documentaries and whatnot. So what we tried to do was think of those as plays to kind of do a better cold study, right, when we don't have data. But people actually rate all these movies and they get pissed off if we show them documentaries all the time. Turns out they actually want to watch Jersey Shore and Keeping Up with the Kardashians, but when they rate movies, they say, oh, food documentary was great. So yeah, there is a material difference.
Yeah.
You should have relation between subtraction of weighted items and WM, like just value 0.01 and 0.05. So I'm curious if you try other values of fraction of weighted data and WM, so that the connection is clear that WM is dependent on the fraction of weighted items.
Yeah, so I didn't try different sparsity values for the Netflix data, but I tried different data sets that I had, and it typically turned out that the weight for the imputed values is always something around that value, so that you get a kind of a balanced data set. So it's maybe not always half as the value of the sparsity, but it's always in that neighborhood somewhere. Yeah. So I don't know if there's some more general truth to it or not, but the 3 or 4 data sets that I tried was always in that range. Yeah.
So there have been a couple of times on Netflix where I've looked at my ratings for a movie in the past and think, what was I thinking?
Yeah.
And I sort of wonder if people's tastes change enough, and if you have data that speak to that, that it might actually make sense to sort of partially impute dated ratings, or movies that were watched a few times in the distant past, rather than treating those as just straight up ground truth.
Yeah, so we do take care of that things that are rated long ago or played long ago, they actually get a lower weight, yeah. Because indeed, yeah, the taste of people changes, or what also sometimes happens is, at the beginning, maybe only the father watches Netflix, and then after a couple of months, he realizes, oh, there are actually kids' movies also, and then all of a sudden the kid starts watching also, right? Things like that. So things always change.
Okay, let's thank
Okay.
Arun again.